All right, so first lesson of physics using distance learning. I'm really excited to teach you guys. I've missed you. So hopefully this goes smooth. I'm going to walk you guys through. It's a lesson that involves a digital lab. So I'm going to be teaching you physics and also teaching you how to use this program so that you can use it on your own independently and get a valuable learning experience out of this. So our purpose for this lesson, I'm going to zoom in a little bit. You should be following along on your notes sheet with me. You should have color coding devices ready to go. Everywhere I highlight, you highlight. Everywhere I write, you write. This is going to be a resource that we use for notes that we're going to refer back to. So the purpose of this lesson is to investigate the variables that affect acceleration. So objects accelerate when they speed up, when they slow down, and when they change direction. So certain variables like maybe, I don't know, mass or force might affect how much an object speeds up or slows down. We're also going to investigate the manner in which these variables affect acceleration. And that's kind of a vague way of saying, do they cause acceleration to increase, or do they cause acceleration to decrease? Or do they just cause no change at all? In which case they wouldn't be a variable that affects acceleration. So a little bit of background before going into this. When forces are unbalanced, and what I mean by that is I have this remote, and when I accelerate it into the air, I'm accelerating it by applying an unbalanced force upwards on the remote. Whenever an object experiences a force that is unbalanced, it's going to accelerate. But what exactly causes the acceleration of the object? So you guys are going to explore this question by running a collection of simulations in the absence of friction. So we know that in regular real life, we constantly are observing the effects of friction. We roll a ball in the grass, eventually it slows to a stop because friction is there. You have a plane flying through the air at high speeds, there is most definitely friction. You drop a penny off of a skyscraper, and there's going to be air resistance that's going to affect the motion of those objects. So whenever we're observing things in real life, we have to remember that there's friction, and it complicates a lot of our problems we're trying to solve. So since we're just learning about forces and acceleration and maybe what the connection is between those two, we're going to assume that there's no friction, or we're going to use a simulation that has no friction. So what you guys are going to be doing is you're going to be using this program I have here pictured on the left that has zero surface friction. I know that it has zero surface friction because this number right here, I can change it, and I have it set for 0.00. That means there's literally going to be zero friction, and I want it to stay that way as I run my trials. So we've got this nice data table that we're going to fill in with some information so that we can see what variables affect the acceleration of this block. So I'm going to make sure that I'm following these first, I guess, the second two columns. I'm going to have my applied force and my mass set exactly for what the column calls for. So the column calls for an applied force of 10, which I have, and a mass of 2. And then it says to push the block. Now, when I push the block, there's the animation at the top that shows me what happens, and it looks like the block is speeding up as it gets pushed. And it also plots the data for the block's velocity on this graph down here. So I even have evidence that with every second, my velocity is increasing by some amount. So it must be accelerating. Now I'm also given my net force here at the top of my simulation. I'm going to motion with my cursor right here. So the program is also doing a net force calculation. Now you might notice the net force is the same thing as my applied force. This is going to be the case for every trial we run because there's no friction balancing out this applied force. So knowing what I know, I'm going to fill in my data table for this first trial. So my net force is 10.0 newtons. Now my velocity time information, this is kind of vague, as to what exactly you're supposed to be filling in. So I'm going to swipe to another page and do a quick review with you really fast here. So this is a velocity time graph that looks a lot like what we have in the program. And when we learned about acceleration, we learned that we can tell from a velocity graph if something is speeding up or slowing down. So if I look at this graph, I can tell that my object is speeding up because every second, the magnitude of my velocity is getting larger and larger. So it must be accelerating because its speed is changing. In this case, accelerating means it's getting faster because it's speeding up. Now, we also talked about how you could quantitate this information. You could describe it with a numerical value, and you can get those numbers from this graph. So the amount that my velocity is increasing for every second or every unit of time is my acceleration. So my acceleration can be found by finding the slope of this line. It's going to be the same as my rise over run, and my rise is how much my velocity is changing, and my run is how much my time is changing. So since we have a velocity time graph here in our simulation, I'm going to motion right here in our simulation, I can use these data points to find my acceleration. I just need to pick two ordered pairs. So my velocity time information is going to be two ordered pairs that are going to help me find the slope. So I'm just going to pick some easy ordered pairs. The first one that I picked is 1 second and 5 meters per second. The second ordered pair, I'm just going to pick the next one, is at 2 seconds and 10 meters per second. Now, to find my slope, I can look at how much is my velocity changing over my change in time. So I could do a calculation. I'm going to use this as scratch paper right here. I know that slope is rise over run. And according to these points, my rise is 10 minus 5 meters per second. My run is my change in time. So 2 minus 1 seconds. So when I simplify this, 10 minus 5 is 5 meters per second, and 2 minus 1 is 1 second. So my acceleration is 5 meters per second every second, or in other words, this object is speeding up 5 meters per second each second. So in my table, I can write that down, 5 meters per second per second. So in your table, what you're going to do every trial is you're going to figure out what's the net force. You're going to pick 2 points from your line, and you're going to use those points to find your acceleration. So I'm going to do trial 2 with you guys, just to make sure that you've got it. So now I'm going to change my applied force right here to 10, or I'm so sorry, to 20. So it was at 10. Now it's at 20. My mass is still at 2 kilograms, so I don't need to change anything there. So I'm going to push the block and see what happens. And right off the bat, I noticed that my line looks like it's a little bit steeper. So that must mean that my block is speeding up, but it's speeding up even faster than it was before. And that kind of even makes sense with some of my personal experiences. If I apply more gas to my car, I'm going to speed up faster than if I don't apply as much gas to my car. So when I apply a greater force, I see that there's going to be, a greater acceleration, so to speak. So I'm going to pick some points now, and I'm going to start recording some data in my data table. So first of all, my net force is 20.0 newtons. That's good. Now I've got to record some information from my velocity time graph. So the first ordered pair is 1 second, 10 meters per second. I'm going to pick my second ordered pair. My second ordered pair is 2 seconds, 20 meters per second. Now I can do this on scratch paper, or I can kind of reason it out. I see once again that I'm going from 1 second to 2 seconds. So my run right here is 1 second, right? My change in velocity though is now a little bit different. Before I went from 5 to 10, which is why I increased 5 meters per second in 1 second. Here, I'm going from 10 to 20. So now I'm increasing 10 meters per second in 1 second. So my acceleration is 10 meters per second per second. So this block is going to go 10 meters per second faster every single second it's experiencing this force. So as you complete trials 1 through 6, you're going to see a pattern start to form, which is going to be helpful on the next page, which is your analysis section. Before you do that, though, I'm just going to point out that for trials 7, 8, 9, and 10, you start to see a difference in your values. And it's very important that you're paying attention to not only how your applied force is different, but also how your mass is different. So for trials 7, 8, 9, and 10, your mass is changing. So let's just do trial 7 together right now. I'm confident that you guys can do 3 through 6 without me walking you through it. But we're going to look at trial 7 and see what's different. So I'm going to reset my simulation. I'm going to change the mass to 1 kilogram because that's what trial 7 calls for. And I'm going to change my applied force to 40. And I'm going to push the block and see what happens. So wow, line is definitely a lot steeper, and I can even see in the program the block is speeding up very quickly. So my net force is 40.0 newtons. My velocity time data, at 1 second, my velocity is 40 meters per second. At my second point, it's 2 seconds, and my velocity is 80 meters per second. So wow, big, big difference here. So in 1 second, from 1 to 2 seconds, my velocity went from 40 to 80. So I'm accelerating, or I'm increasing my velocity by 40 meters per second in just 1 second. So my acceleration is 40 meters per second. So that's interesting because that's a very different value from what I saw in trial 1 and trial 2. So I'm going to do trial 8 and see if the same pattern kind of holds, because it looked like for trial 1 and trial 2, I saw an increase in acceleration. Let's see if when I do trial 8, I also see an increase in acceleration. So I'm going to change my mass of the block from 1 kilogram to 3 kilograms, because that's what trial 8 calls for. But my applied force is staying at 40. So I'm going to push the block and see what happens. Okay, that was a little bit different because my line is not as steep, and I could even see from the program it didn't seem like the block was speeding up as much as it did before. So my net force is still 40.0 newtons, but my ordered pairs are going to be a little bit different. So my first ordered pair is saying that at 1 second, the block was going 13.33 meters per second. At the second ordered pair, at 2 seconds, the block was going 26.67 meters per second. Geez. So my values are very different. I'm seeing that from 1 to 2 seconds, I definitely didn't go as fast as I did in my previous trial. I went from 13.3 meters per second to 26.67 meters per second. So I increased by 13.34 meters per second in just 1 second. Now I'm doing that math in my head, but you might want to do it in a calculator or with scratch paper, and that's okay. But my acceleration is much smaller than it was in the previous trial. So if we really think about this, mass is just a measure of an object's inertia. It's resistance to changing its motion. The more mass something has, the more it's going to resist changing the motion it's already in. So when we talk about this block, right, a 1 kilogram block versus a 3 kilogram block, the 3 kilogram block is going to resist speeding up more than the 1 kilogram block is. So when I use a 40 Newton force on both of these blocks, I'm going to see the object with less inertia, the 1 kilogram block, is going to speed up much more than the block with more inertia, the 3 kilogram block, because it's going to resist changes in motion more. So you guys can complete the rest of the trials in this data table now and see if maybe there's some patterns in the manner at which acceleration is changing, because we kind of reasoned through, does this make sense? And it does make sense, the evidence that we're seeing, but That's just part of the lesson. The other part, the very, very important part, is the manner in which acceleration is increasing and decreasing. Is there a numerical pattern that we can find between our mass, our net force, and our acceleration? So I'm going to leave you guys to that to complete the rest of the trials. When you're done with the rest of the trials, the next slide or the next page in your notes is going to have you looking at those numbers and looking for a quantitative pattern, a numerical pattern in which acceleration, force, and mass are all changing. And you're going to be asked to identify a set of trials that make your point or make your case or support your answer. So when you're asked to indicate the factor by which acceleration increases or decreases, what this looks like is, for example, if net force doubles, aka it's multiplied by 2, maybe, I don't know, just maybe acceleration is going to increase, right? It's not enough to say acceleration increases. That doesn't tell us the manner in which it increases. So a more accurate way of describing how acceleration increases is saying that when net force doubles, acceleration also doubled. What? No way. You're going to have to look at your data and see if it actually does that and double check. But let's say that acceleration didn't increase. Let's just say that this was a situation where acceleration decrease. Let's say that there's a set of trials where you're looking at something like that. Instead of saying that it doubles or triples, you could say that it is divided by 2, or maybe divided by 3, or cut in half, or cut into a third. There's a lot of different ways verbally that you can say it, but mathematically, what I'm going to be looking for is just, was it multiplied by a factor, aka a number, or was it divided by a number? So as you complete this, you're going to want to check that you did it correctly, because once again, this is a notes sheet. I don't want to rob you of the experience of learning as you're doing, though. So I'm going to have the answers for your notes posted on my website so that you can double check, did I get the right message out of this? Did I learn what I was supposed to out of this? And then your practice is going to be online, so you can really put into practice what you learned from this lesson. So hopefully this was clear and concise, and if you have any questions or concerns, you can always just reach out. Have a great day.